Okay, we are recording. All right, so you want to see the quiz. Quiz number 8. All right. Okay. This is when I wish I could upload some stuff. I'm sure there's a way to do it, and I just don't know how. Okay. So it wanted you to use the table, and can I? No, I don't think I can. Okay, so they want you to use the table to figure out. Let's start with abs. So this is quiz number 8. Starting off by finding the absolute extrema of f of x and where they occur. And so, what do we have? We've got down at the bottom of this little, you got 2 tables, right? So I would start by looking at the table for f prime of x. I'm looking at the bottom table, and it says for when x is between 0 and 1, you've got positive, and then between 1 and 2, you've got a negative, and between 2 and 3, you also have a negative. So that means that the graph will be increasing here, decreasing, and then decreasing. And so that means here you're increasing and then decreasing, which means that you have a max at x equals 1. And then we've got endpoints, right? And so, okay, here, let's do this. I'll do a number line instead of it showing it like that. Let's go with, we've got an endpoint of 0 and another endpoint at 3. And then 1 and 2. Okay, so it said it was increasing and then decreasing and then decreasing. Okay, so the fact that it's a left endpoint and then decreasing or increasing means that this would be a local minimum, and then it goes up and then it starts decreasing, so this guy is a max, and then it keeps on decreasing, and here's an endpoint, and so this also is a minimum. But they wanted to know absolute, right? So this one is definitely our max, and then which one of these guys, either x equals 0 or x equals 3 are mins. And so what you want to know is what are your y values. But we have a table for that. On the first table, it says x and then f of x. And so that's your y values. So we've got at x equals 0. I don't know why I shouldn't draw that line because I don't think it's 0. Okay, so at x equals 0, your y is 0, and at x equals 1, your y is 2. 2 we don't care about, it didn't affect anything, but then when x is 3, we've got a negative 2. And so your maximum, you only had the one max, right? So the max happened at when x was 1 and y was 2, but the minimum, which one's smaller? Is 0 or negative 2 smaller? The smaller y is definitely negative 2, and so you've got these are absolutes. Absolute, absolute. Absolute minimum is going to happen at 3, negative 2. So this guy is a local minimum, but it's not the absolute minimum. All right, so that was that. Points of inflection, what you've got to do is look at the second derivative. And so for points of inflection happen when the concavity changes. And the concavity changes when the second derivative goes from either positive to a negative or a negative to a positive. So when I look at the table and it gives me second derivative for each of those intervals is negative and then negative and then negative, right, for each of the intervals. So this was from 0 to 1, and this was from 1 to 2, and then from 2 to 3, right? That means it's concave down the entire time over the whole interval, over the whole thing. And so it didn't change concavity, and so there's none for no inflection points. There are no inflection points. So that was part B, and then to sketch a possible sketch. So we definitely had some values that they gave us, yeah. So part C. So it gave us this, and got toot, toot, and a 1, 2, 3. Okay, so in that table, they gave me x and f of x, right? So that's your x comma y. So we have 0, 0, we have 1, 2, we have 2, 0, and then 3, negative 2. So those are the points they gave me. And then concave down the whole time, right? And there's also this part that says, and then we already talked about here, like this was the max at 1, 2. This is a local minimum at 0, 0. And then this is the absolute minimum there. Concave down the whole time, which tells me it looks like this. And then from here, it should look like that. The other thing that tells me this is that if you look at f prime of x on the table, right, at x equals 2, it says f prime does not exist, which means that you should have a cusp or a corner there. And so that makes sense there too. There's your little cusp that's happening. Okay, so hopefully that makes sense. All right. Okay, a few things. Justin wrote me a novel. Yay. During a second derivative test, do you use critical points? You're welcome, Maddie. Okay, during the second derivative test, do you use critical points from the first and second derivative to find concave up and down? Second derivative test, what you are going to do is you're going to find the first derivative, find f prime, and the x values, those critical points, right, when f prime equals 0 or doesn't exist, right? So these are what you call those critical points or critical values. Then you're going to find the second derivative, and then you're going to plug in these critical points into the second derivative. And then if the second derivative is a positive number, then that means you're concave down, right, which means that you've got a maximum. No, sorry, being an idiot. You're concave up, dummy. Just kidding. Concave up like a cup. Up, positive, up like a cup. Up. Concave up when it's positive. And so then that's a, down here is a minimum. And then if f, the second derivative, is negative, then you're concave down, which means that that critical point is a maximum. Yeah, so you're using the critical point from the first derivative, but just plugging it straight into the second derivative. That's second derivative test. Okay. When you're creating a number line for, let's say, okay, so hopefully that makes sense now for second derivative test. Okay, so then when you're creating the number line for the plus or minus thing, do you plug in x values into the derivative in order to find the positive and negative y? Let me see if this answers your question. If you're going to use the first derivative test, you find the first derivative and you draw a number line and you've got your critical values, right? And you're plugging in x values into, this is why I always wrote f prime next to my number line if that's the number line that I'm plugging it into, right? And we get, let's say, plus, minus. These are x values, like let's say, I'll make up numbers. Let's say this is a 0, a 1, and a 2. I would plug in, to figure out this guy, I would plug in x equals -1, and whatever f prime is, I'm saying that it's a positive number, I made it up, right? Then that means that it's positive. So it's the y value, but the y value of your derivative equation, not the original equation. And then here, let's say, well, that would not be friendly, but I would plug in a, what, 0.5 or a 1/2, and I said, oh, okay, now it's a negative value. And then here, I really chose nice. Good thing I don't have to actually plug it in. Your f prime is positive, and then here, anything to the right of 2. So let's say I plug in a 3 into the derivative, and then here I'm saying the derivative is negative. Then, if you're at, when you go to find the max or the min, when you're saying max or min, right? We're saying locals right now. This would be increasing to decreasing. Then you've got an ordered pair for your max, right? And so it would be 0, and then this guy is the y value for when x is 0. So y value for f of x, not the derivative. So your maxes would be there and also at like 2, and then I'm plugging 2 into the f function to figure out your y values. Remember, your maximum is happening on your graph, right? So maxes and mins do that. So hopefully that is what you were asking, Justin. You're typing. Okay. All right, then the next question is, okay. All right, can you do 19 from the last worksheet and 10 from the quiz? So 19, I'll do 10 from the quiz while you answer my question of, oh, I don't need to do 10 for the quiz because I just did it. Where was my directions for second derivative test? This was number 10 from the quiz. Now, how do you find the local extrema using second derivative test? You do that. Okay, but then number 19 from the last worksheet, are you talking about? Okay, it must be that one from the multiple choice one. Thinking it must be. Did the other one have 19 questions? No, it did not. Okay, perfect. So 19 from the multiple choice. Okay. Boop. So multiple choice worksheet number 19. All right, use the graph of f above to estimate where f double prime is 0, positive, and negative. Okay, so they give you this graph of f, and I'll try my best to look something like that. And this is the graph of f. Super important. It's very rare for them to give you f and not something else, right? All right, so 19 says, use the graph of f above to estimate where f double prime is 0, positive, and then negative. All right, so when it's 0, it's an inflection point, meaning it has changed concavity. When it's positive, it's concave up. And when it's negative, it's concave down. All right, so to me, this looks like it is concave down from here to here. And then, so from here to here-ish, concave down, which means it'll be negative on this x interval, right? And then it looks to me like it is concave up from here to here. So from here to here, concave up, which means that somewhere where it's changing is when it's equal to 0, because that's, I'll say that's your inflection point. Inflection point. Okay, so when I'm looking closer at the graph, it looks to me, oh, I drew it. It looks like it's right there on the x-axis. So it looks to me like it is an inflection point. So f double prime equals 0 when, it looks to me like when x is 0. And then f double prime is positive when it's concave up. So when you're on this interval from 0 to infinity, and then concave down or negative when you're negative infinity to 0. That would be D. Question 9 on the quiz, all the way. All right, here we go. Okay, so they gave you this graph of, I'll try to draw it. It's, okay, we're crossing 0 here, 0 here, and 0 here. And you're like up here, and you're down here. And then up a little bit, and then down, and bouncing back up, and then something like that. Okay. It's messy, but whatever. Okay, so you're on this closed interval from -3 to 3, and this is f prime. Super important that you identify that, okay, they have given you the derivative graph. They are not giving you f, they're giving you the derivative. And so, for what values of x in the open interval does it have a relative maximum? All right, well, let's go ahead and draw this sign chart of what's happening with the derivative. We've got -3 to +3 is our closed interval. And then the derivative is changing signs here at -2 and at 0. And then, well, there's a 0 here at 2. I guess we could put the whole thing, but anyway. Okay, so first derivative, right? Is it positive or negative? Well, you're looking at the first derivative. So when is it above the x-axis versus below, right? So this is above x-axis, then that means it'll be positive. And when it's below the x-axis, then your derivative is negative, right? We're looking at that. So since this is the graph they gave us f prime. So from -3 to -2, your graph of f prime is above the x-axis, so it's positive there. It's below the x-axis between -2 and -1, and also between -1 and 0. And then it's above the x-axis between 0 to, oh, I left off 1, whatever. And it's positive again, it's still above the x-axis. And then it is still above after, so from 2 to 3. So there's your f prime. So when is it going to have a relative maximum? So a relative maximum happens when you go increasing to decreasing, right? So when f prime goes from a positive value to a negative value, or from increasing to decreasing, another way to say it, right? So, and the only place that that happens is right here at -2, right? You see that you're going a positive to a negative, which means your graph is, the graph of f will be increasing and then decreasing. And so you have at x equals -2, and that's the only spot that it went from a positive to a negative. So at x equals 2, since the graph of f, not f prime, but graph of f is goes from increasing to decreasing, and also f prime of -2 is 0, so -2 is a critical point there, and the graph of f is going from increasing to decreasing, then at x equals -2, you've got a relative max. Okay, that was part A. Let me just scroll down and make sure you guys don't have any questions about what I just did right there. Okay. All right. Part B. Now they want to know, where does it have a relative minimum? You know, and so can I cheat, and I'm going to erase this part, hopefully, so that way I don't want to have to redraw my graph. Okay, so I'm going to take this and try to erase it. Come on, please work. Please work. Please work. Doop. Did it select it all? Nope, of course not. Oh well, I'll do it in peace. That. Bye. Almost so close. Delete. Come on, you. This is still faster than me having to redraw the graph again. Come on. Almost. Doot. Okay, delete. Yes, okay. Part B. Part B wants to know relative minimum. So relative minimum is going to happen when your graph goes from, when f goes down and then comes up. So when the f prime goes from negative to a positive. And that is happening right here. You see how it went from a negative to a positive, which means your graph is going down and then coming back up again. Yeah, so it'll happen at x equals 0. So your relative minimum is at x equals 0 since the function goes from decreasing to increasing. And your derivative at 0 is 0. So 0 is a critical point since f prime of 0 is 0, and then also your function is going from decreasing to increasing because the slope, or f prime, is going from a negative to a positive. All right, then they want to know, when is the graph of f concave up? And then justify your answer. All right, I'm going to try to delete these again because it's still faster. If I can actually grab them all at one time, that would be much better. Okay. Here we go. Please. Oh, I think I might get it. Delete. So close. It left off my little thing. Okay, come on. You go away too. Go away. Come on, you. There we go. That'll select it. Delete. Thank you. Okay, now part C says, where is it concave up? All right, so F is concave up when your second derivative is positive. You were given f prime though, right? Well, f double prime is the slope of f single prime, of the first derivative, right? So what we want to know is, when is the slope positive of the graph they gave us? Yeah? So to me, this is what I see. I see the slope is negative 0. I'll do a different color now. Positive slope here, 0. Negative slope, 0. And then positive slope again to there. So I'm going to draw a number line for second derivative number line. We've got it's negative from -3 until -1, and then from -1 to 1 it's positive. From 1 to 2 it was negative, and then from 2 to 3 positive. And so your concave up on this interval between -1 and 1, and again from 2 to 3. And that's because the slope of f prime, the first derivative, is positive on these guys. So concave up on, on the interval from -1 to 1, and again from 2 to 3. And that's since you can say the slope of the first derivative is positive on these intervals. And then part D, I'll draw you what I did. I put all of this together, and we've got doot, 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 and doot, doot, doot. Okay, so they gave us the point -3, 0, that when x is -3, y is 0. I know that there is a max at -2, and I know it's increasing from -3 to -2. I know it's decreasing from -2 to 0. And I know there's a minimum here at 0. And I know that it's increasing on the rest of the interval from 0 to 3. I know it's concave down from -3 to -1. I'm talking about concave down. I know it's concave up from -1 to 1. Concave up. And then it's concave down from 1 to 2. And I know it's concave up from 2 to 3. All right, and I know that this is an actual point there. So we want maximum here. So let's say I go to there. I need, it's going from concave down to up here. This is an inflection point here and in between there also. So you go up and it's concave down. So we'll go like that. And then it's concave up. So I went from like that. This is still connected. And then it was concave down, but then it went to concave up. And so that's the graph I did on there. Okay, that was number 9 from the quiz. Hopefully, let me just scroll down and make sure you guys didn't have questions specifically on that. Nope, okay. A question similar to quiz number 8. I don't know, you find me another one. I don't have time to flip through the book and find stuff, so 7 from the quiz. All right, quiz number 7. All right, find the function with the derivative is 3x squared minus x plus 1 and passes through the point 2, 13. All right, so this is the antiderivative question with the c, right? That you need to find the actual c value. So f of x would be, what do I do to find the antiderivative of this? You're doing reverse pop and drop, right? So reverse pop and drop, you're going to take that, come over here, the 3x squared, and you're going to add 1 to the exponent, add 1, which will give you a 3, and so then divide by 3. You divide by whatever you end up getting in that exponent. Well, then that means that it's a, what would that be? A 1x cubed. Double check yourself. If you pop and drop on x cubed, will it give you 3x squared? And it does. And then the negative x, this has like to a power of 1. And so you add 1 to your exponent, because we're doing reverse pop and drop. Instead of subtracting 1, I'm adding 1. And then you divide by that exponent. So divide by 2, which tells me that this would be a -1/2 x squared. Double check yourself. If you do pop and drop, right, you would pop that 2 in front. You would get a -2/2, which is a -1, and then you would drop the exponent by 1. So this is a -1/2 x squared. And then the 1, you can think of it as 1 times x to the 0 power. And when you add 1 to the exponent and then your new exponent is a 1, and you divide it by 1, then the antiderivative of 1 is just x to like the power of 1. So we got plus x. And then don't forget plus c. Yeah, because there was some constant there that when we took the derivative of f, the derivative of a constant is 0, so it went away. Then you plug in these guys. Plug in 13 into f of x and plug 2 into your x. And then solve for c. So that's what? 8 minus 2 plus 2. And so those guys go away. 13 minus 8 is 5. So 5 is c. And so your function is f of x equals x cubed minus 1/2 x squared plus x plus 5. There we go. All right. Hopefully that makes sense. 20 from the multiple choice worksheet. Okay. Use the given derivative to find the local extrema of the function. All right, so y prime is x plus 1 times x plus 3. So to find the local extrema, that's local maxes and mins, set it equal to 0, and setting each factor equal to 0 gives you that your critical points are -1 and -3. And so you draw the number line. This is y prime. I put -3 is actually to the left of -1. So you do have to be careful that you know your number line, right? All right, so there's that. And then you're plugging in values in between, right? So let's go with, if I go something to the right of -3, if I plug in x equals -4, then your y prime will be -4 plus 1 times -4 plus 3, which is, I don't care about the actual value, I just want, it's a negative value times a negative, which will give you a positive. So this guy is positive in this interval. If I plug in something in between -3 and -1, let's go with x equals -2. Your y prime would be -2 plus 1 times -2 plus 3, which is a -1 times a positive 1. A negative times a positive will give you a negative. And then something to the right of -2, -1, let's go 0. So then your y prime will be a 0 plus 1, positive, 0 plus 3, positive, definitely a positive. And so, what do they want? Local extrema. Well, you're going to go from, I still always have to do this, you're going to go from increasing to decreasing to increasing. So here is a max and here is a min. So a local max at -3, so that's your max at x equals -3, and then at x equals -1 will be your local min. All right, that was 20 from the multiple choice, 22 from the multiple choice. The graphs below show the first and second derivatives for a function. Select a graph that passes through point P. All right. So multiple choice, 22. They give you f prime is this guy, whoops, and f double prime is this. Yeah! Pretend like that's straight. And then point P is somewhere here. Let's see, point P. Okay, so what does this mean? This means that the graph of F will be increasing from in negative infinity to 0, and it'll be, sorry, lying to you. Let's go back and pretend like none of that just happened. I was just pulling a Calc BC student and looked at that graph like it was F, and it's not. It's F prime. Okay, we have a 0 and a 0. You are below the x-axis here, so your F prime is negative. And then from here to here, F prime is positive. And then from here to infinity and beyond, F prime is negative. You know, so if I do the F prime chart, whatever that value is, and whatever that value is, right? We've got a negative, and then a positive, and then a negative. All right, so what that means is that the graph of F is decreasing up until whatever value that is, yeah? And then it's increasing, and then it's decreasing. Come over here to F double prime. Here it's saying that your your second derivative is positive because you are above the x-axis here, and then here your second derivative is negative. So this one at least is easy. At 0 you've got positive and then negative, which means you're concave up to the left of 0 and concave down to the right of 0. All right, so which one? Well, you've got you should have F is decreasing to here, F is increasing to there, and then F is decreasing, like something like that, and concave up to 0 and concave down to the right of 0. So that looks like B to me. Sorry, I messed that up right at the very beginning. But yeah, you're looking at above or below. So here, it's worth the writing it since I goofballed it. So, different color. Let's go with blue. Okay, so here, you're from here to here above the x-axis. And then do what? Green. Sounds good. You've got from here to here below the x-axis, and from here to here below the x-axis. So when you're looking at whether it's positive or negative, you're looking at below or above. Same thing here. Above x-axis, which makes F double prime positive. From here to here, below x-axis, which makes second derivative negative. All right, that was 22. Number 7 from review worksheet. Are you talking about the multiple choice one or the non-multiple choice one? Number 7. Okay, yeah. Sounds good. So this is 5A review, number 7. Okay, It says f is continuous on 0, 3 and satisfies the following. Find the absolute extrema of f and where they occur. Okay, so I'm going to look at f prime for the extrema, and I'm going to turn this table into a sign chart. So we've got from 0 to 1, it told me it was negative. From 1 to 2, the chart tells me that the first derivative is positive, and then from 2 to 3, it says it's positive. Okay, so I'm looking at the second chart where it gave me the plus or minus signs for f and f prime. So the absolute extrema and where they occur. So you've got this guy is an end point, right? And you're decreasing, increasing, still increasing, still increasing, increasing. I'm going to run out of room, but whoops, pretend like it didn't just go down. But increasing all the way. Oh, shoot. Okay, well, at least I'll be able to fix it. Okay, so you're starting at a left end point and you're decreasing, and then you're increasing, 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 increasing to this end point. Okay, and I went way high, but I don't know that it's way high. So that means that at 0, these are locals. I don't know if they're absolutes yet. We have a local max at 0. We have a local min at 1. And at 3, we have a local max. Yeah. And so then the absolutes, well, there's only the possibility of 1 being the absolute min, right? But for maxes, what you got to do is look at the other table that says they give you x and f, right? So it says when x equals 0, your y value is 0. When x is 1, they said y is negative 2. And they said when x is 3, the table tells me y is 3. Yeah? So this guy is your absolute minimum, which we already figured that out from, it's the only minimum that showed up here, right? So 1 comma negative 2 is your absolute min. For your absolute max, which one's bigger? Y equals 0 or y equals 3? And so 3 is definitely bigger than 0. So this is your absolute max is going to happen at 3 comma 3. All right, so that's that. For points of inflection, you want to look at when does the concavity change, which means that when does the second derivative change signs. So this is still number 7, but part B. Points of inflection happen when concavity changes. Which means that your second derivative goes from positive to negative, or from a negative to a positive. And so I look at this chart and I look at the line for the second derivative, and it says positive, 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 which means that this graph is concave up over the whole graph. Or I should say over the entire interval. Over the entire because they're saying f between 0 and 3. So over the entire, I'll just say graph. Just because that's all we're talking about is this guy. So no inflection points. Which means none, but no inflection points. Don't think that you're always going to get no inflection points. All it's got to do is change signs, here, go from a positive to a negative or a negative to a positive. Okay, then you've got an inflection point when it changes. And then sketch a possible graph. Okay. Let's see. I've got Let's see if I can do this without an answer. Where are we going? We're going from 0 to 3. And okay. So 0, 1, 2. Oh, shoot. Okay. Let's go. 0, 3. So a 1 and a 2. Okay, so we got 0, 1, 2, 3. So here's my y-axis. And we're going to go up. Oh, and then I made it too big. Oh well. 3, 1, 2, 1, 2, 3. And then -1, -2. Okay, so I'm first going to plot the points they gave me for the graph. They gave me that when x is 0, y is 0. When x is 1, y is -2. When x is 2, y is 0, and when x is 3, y is 3. So those are for sure points. We have, let me go down here. Between 0 and 1, I've got that a negative slope. So you're decreasing from here to here. From here to 1 to 2, you're increasing. And from 2 to 3, you're increasing. We've got concave up the whole way. Let's say everywhere. It doesn't mean it needs to be one giant concave up like you saw in the quiz. You could do it in 2 different sections, which is what's going to happen. And the reason why I know that is there is a does not exist here at when x is 2 for the first derivative and the second derivative. So that means there's got to be a cusp or a corner there. And so, and the fact that it's concave up means it's going to be a cusp. So we go up, concave up, and then concave up. That's how I would draw it. There's a possible graph of it. Okay. That was 7 for review. An example of the mean value theorem pictorially or graphically? Yes. Let me do this. If I give you a graph that looks like that, right? And these are endpoints. The mean value theorem says that if I find the slope between A and B, and I'm going to all right, so let's say I find the slope between A and B, right? Which is, so the slope between A and B is the slope you have known your entire life, because it's a straight line. It's the slope between 2 points. It's going to be your y minus y over x minus x, right? Your book says f of b minus f of a all over b minus a is how your book says it. But regardless, it's the slope between 2 points. Mean value theorem says that if you have a continuous function on the closed interval and a differentiable function on the open interval, which means that we don't care about these endpoints, about them being differentiable. But if you're continuous and differentiable on this interval, then there is at least one x value that has the same slope, so that the slope is parallel. Yeah. So let me do a different color. I see 2 spots. I see right. Well, and of course I didn't. Let's see if it'll let me grab it and move it. I didn't. Can I move you? Oh yeah. There you go. Boop, right there. that right there, the slope of the tangent line, so this guy right here is f prime, the derivative of f at, I'm going to call it c. And what it's saying is the slope of the tangent line to this point here, to this c value, is equal to the slope between the 2 points. There's also another spot, by the way, and it is, if I can get it to, all right, that's not bad, something like that. It's over here. So here, I'll move it a little bit, fix it, there we go. That looks like it will work. So here is another spot where the derivative of the function, evaluated at whatever this x value is here, is going to equal, it has the same slope, parallel slope, right, as the slope between a and b. So that is mean value theorem. There is at least one spot, if not more, and you just find where are these lines parallel. All right, that is mean value. This is, I guess I should have titled it. This is mean value theorem. What it means graphically or pictorially. There's this one. This graph has 2 spots. Number 13 on that review worksheet is the same type of problem. So 5A review worksheet, not the multiple choice one, but number 13 gave you inverse sine. Something like that. My graph sucks, but, and then we wanted you to draw on this graph which ones satisfy the conclusion of the mean value theorem. And so if that is the slope between your endpoints, right, then I've got, it looks to me like there are 2 spots. My graph sucks, but it looks like right about there and right about there are 2 spots where when you find the derivative of f and you evaluate it at those x values, they'll end up having the same slope as if you found the slope between the 2 endpoints. Mean value theorem. All right, that's that one. 14. All right. Change that to that. We got 5A review, number 14. All right, so they want to know all the following functions satisfy the conditions of the mean value theorem on the interval from -1 to 1. So satisfy conditions. Another way to say it is the hypothesis of the mean value theorem on the interval from -1 to 1. So if it's fine in between there, then it doesn't matter. But I mean, if it's fine outside of there, then it doesn't matter. But so the conditions are continuous. It needs to be continuous on -1 to 1. And then it needs to be differentiable. So on the open interval from -1 to 1, which means no corners, no cusps, no vertical tangents, things like that. So first one is sine of x. All right, well, we know sine of x looks like this. Yeah. And it's definitely, and then that's over the whole thing. And so from -1 to 1, all right, so that means it goes like this, right? And so definitely continuous on this guy. It's continuous over the whole thing. So, and it's differentiable. So it's continuous over the whole thing. It's differentiable over the whole thing. And so this guy is not the one that is not true. Inverse cosine graph looks like it's from 0 to pi. Let's see if I remember. Okay, so it'll go from up to pi. It'll be a -1, and it'll be a +1, and a pi over 2. So here, 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 and looks like that. There's inverse cosine graph, yeah, and this is part of the reason why we don't care about that it's got endpoints, right? But inside of it, definitely continuous, definitely differentiable. X to the 5/3. Well, that one's not as easy to figure out, huh? So, and I ran out of room. Okay. The graph of this, you could do some, well, you don't even have a calculator. Well, I know at -1, I'll be at -1. I know at 0, I'll be at 0. And at 1, I'll be at +1. What I really need to know is what happens in between, though. All right. It looks something like that. This guy is also, it's continuous and it's differentiable. Let me go to a new page. D was x to the 3/5. And then E is x over x minus 2. Okay. So this guy ends up looking like this. And so this guy has a vertical tangent at x equals 0. So this one is not going to be not differentiable at x equals 0. This guy has a vertical asymptote at 2. It's going to look like, and it's got a shift, right? Yeah, it's going to look like this and like that, something like that, right? I think it's a shift up, but you're carrying, the only thing you're caring about is from -1 to 1. So this one is okay. This one is continuous and it's differentiable. Yeah, that vertical tangent one is not easy. I would say that something like that would probably be more on, something like this would be on something that you would have a graphing calculator. One thing that I would expect you to know is x to the 2/3. This guy is a cusp. So you can think about it as if you have y equals x to the 1/3, which is rad x, no, cube root of x. It looks like a sideways swimmer stroke, like that. But then when you square it, what that does is it takes these guys and turns those negative y values positive. So this guy is a cusp at x equals 0. But the other things I feel like, and even that, I don't know that we ask you to know that just by hand, but hopefully eventually by the AP exam you'll know it. But yeah, you probably don't have to worry about that. It was more of, yeah, I don't have a good answer for you. You do need to know when you need to be, it'll probably be an easier function is all I'm going to say. But you do need to know which ones, how to figure out when it satisfies the mean value hypothesis versus not. And that's the whole continuous and differentiable. Okay. Number 7 from, okay, I already did number 7. How are you doing? Okay, I told you. Okay, I think, oh, we're past time, aren't we? Okay, we are. All right, good luck. You guys asked fabulous questions. Fantastic questions. Just double check that I didn't forget anything else. No, you guys asked incredible, perfect questions. This was a great GVL. So I think you're all going to do very well if you end up understanding all of the things we went over today. So, all right, good luck. I'll see you tomorrow. I'll put the link to the recording in the window in just a second.